Welcome to Daily Papers, the podcast where we break down the latest and most interesting academic papers into something you can actually understand.
Today, we're looking at a big problem in the world of AI. You know how we want chatbots like ChatGPT to be able to read an entire novel or a huge legal document and then answer questions about it instantly?
Exactly. We want them to have a massive context window, which is just a fancy way of saying a really good short-term memory. The dream is an AI that can handle 1,000,000 words of context or more. But there's a big, slow bottleneck holding us back.
And that bottleneck has a name: attention. Every time an AI generates a new word, it has to perform an attention step where it looks back over the entire context to figure out what to say next.
Imagine you're writing an email. For every single word you type, you have to stop and reread the entire email thread from the beginning. If that thread is 1,000,000 words long, you're not going to be writing very fast. That's the problem these AIs face.
So, to solve this, we throw our most powerful computer chips at it: GPUs, or graphics processing units. These are the same chips that power high-end video games and are the workhorses of the AI world.
But according to a new paper, that's exactly the wrong tool for the job. The paper is called AMMA, a multi-chiplet memory-centric architecture for low-latency 1M context attention serving, and it comes from a team of researchers at UC San Diego, Samsung, NVIDIA, and other top institutions.
And their core argument is that using a GPU for this attention task is a massive mismatch. A GPU is a computational beast designed to do trillions of math calculations per second. It's like a Formula One race car engine.
But the attention task isn't about doing a ton of math. It's mostly about fetching huge amounts of data from memory very quickly. The researchers call this being memory-bound, not compute-bound. So we're using a Formula One engine to make a trip to the corner store. The engine is powerful, but you spend most of your time stuck in traffic.
And the result is that the GPU's powerful calculators, its compute units, are sitting idle over 95% of the time. But even when they're idle, they and all the machinery around them are still switched on, drawing a massive amount of power. It's incredibly inefficient.
So these researchers asked a radical question. What if instead of building our chip around a powerful but underused processor, we built it around what the problem actually needs: memory? What if we created a memory-centric architecture?
Okay, what does that actually look like? Are we just talking about a chip with a giant memory bank on it?
It's much cleverer than that. They call their design AMMA. Imagine a modern chip package. Normally, you'd have a big GPU die in the center. The AMMA design throws that out. Instead, they fill the package with special memory cubes, 16 of them to be exact.
So it's all memory? Where does the processing happen?
Right there inside the memory cubes. This is the key idea, called processing near memory, or PNM. On a special layer of each memory cube, they add a small, efficient processing engine.
Ah, I get it. Instead of the data having to travel all the way from the memory to a central processor and back again, the processor is right there where the data lives. It's like putting a personal chef in every aisle of the grocery store. No more running back and forth to the main kitchen.
That's a perfect analogy. And because they filled the chip with these smart memory cubes, the total memory bandwidth, the speed at which they can read and write data, is just enormous. They've essentially doubled the bandwidth compared to a standard GPU setup.
But having 16 little chefs all cooking at once sounds like chaos. How do you coordinate them all so they work together efficiently on the same recipe?
This is where the other clever parts of the design come in. First, they developed what they call a two-level hybrid parallelism scheme. It sounds complex, but the idea is simple. Instead of having all 16 memory cubes trying to talk to each other at once, which would create a massive communication jam, they group them into 4 small teams of 4.
Like different departments in an office.
Exactly. For most of the task, the cubes only need to talk to their teammates within their own little group. This keeps communication local, fast, and avoids clogging the network. They only need to communicate across the whole company, so to speak, right at the very end.
Okay, that makes sense. Divide and conquer.
Then they took it a step further. They redesigned the workflow, which they call a reordered collective flow. They basically looked at the order of operations and realized that if they shuffled a few steps around, they could completely eliminate several rounds of communication and make one of the final steps much simpler. It's like realizing you can do all your chopping before you start cooking, saving you multiple trips to the cutting board.
So it's a new hardware design, a new way to organize the work, and a new, more efficient workflow. It's a complete rethinking of the problem.
And the results are pretty stunning. They compared their AMMA design to one of the most powerful GPUs on the market today, the NVIDIA H100.
And the verdict is?
This for specific, crucial task of long context attention, AMMA is up to 15.5 times faster.
15 times. That is a huge leap.
It gets better. Because the design is so much more efficient and doesn't waste energy on idle compute units, it uses almost 7 times less energy to do the same amount of work.
Wow, so we're talking about a future where an AI can read and understand a million-word document, not just a little bit faster, but in a fraction of the time and using a fraction of the electricity.
Precisely. This could be a game changer for everything from legal tech to scientific research. It shows that sometimes the best way forward isn't just to build a bigger, more powerful engine, but to step back and design a completely new vehicle that's perfectly suited for the road you're on.
So by focusing on memory instead of raw computation, the AMMA architecture presents a whole new path for building the hardware that will power the next generation of AI.
That's the takeaway. It's a reminder that the biggest breakthroughs often come from challenging the fundamental assumptions of how things are done.
And that's all we have time for on today's Daily Papers. Join us next time as we unpack another piece of cutting-edge research.